The limitations of physicists who cannot design or decorate the world without the help of mathematicians. Physics is a discipline that studies matter, forces, energy, motion, and space-time to understand how the universe moves. Mathematics, on the other hand, is the language used to uncover the secrets of nature. The phenomena that physicists observe ultimately occur because of invisible forces and laws. How should these invisible things be described, and how should they be written? It is at this point that mathematics appears. As mathematicians observe nature, they first look for visible patterns. However, by relying on sight alone, the common flow shared among patterns, that is, the pattern itself, often does not become clear. At moments like this, mathematicians assign numbers and letters to each pattern. They organize the relationships between them and write them down as an expression, like a single sentence. This expression is called a relational formula. When many different numerical cases are grouped and expressed using a single letter, such as X or Y, it becomes possible to move beyond the specific phenomenon that is directly seen and summarize everything at once as a law that holds in any situation. From this point on, the work belongs to physicists. They observe motion, light, electricity, and waves unfolding before them and think, the world moves according to relationships like this. Then, through experiments and observations, they continuously refine those formulas. So, from a physicist's perspective, mathematics is not merely a tool for calculation, but a language for quantitatively designing laws and rendering those laws more clearly and precisely. For a physicist, numbers and letters are the minimum pencil required to bring invisible forces and laws up onto the page. It would not sound strange for a physicist to say this: without the formulas and symbols refined by mathematicians, a physicist cannot properly design ideas nor decorate them with clarity and elegance. Classical mechanics deals with the relationship between the forces acting on objects and their motion. Newton looked at a falling apple and the orbits of planets together and wanted to discover a law that could explain both the Earth and the heavens at the same time. To write down that answer, he even created a new mathematical tool called calculus. As a result, it became possible to calculate, using the same mathematical equations, why a ball thrown at an angle traces a parabolic path, where the ball will land, and how the orbit of the moon revolving around the Earth is maintained. In electromagnetism, the central question is how electricity and magnetism are related to each other. Maxwell organized countless experimental results and laws into 4 concise equations, showing that electric fields and magnetic fields are in fact a single electromagnetic field. Based on these equations, technologies such as radio waves, radar, medical imaging, and smartphone communication emerged one after another. A mathematical formulation once established thus became a seed that generated new technologies over a long period of time. In the case of relativity, the role of mathematics appears even more explicitly. Einstein presented a completely new perspective. Gravity is not a force, but the result of mass causing space-time to curve. However, to describe curved space-time with precision, Euclidean geometry alone, built on the assumption of flat space, was insufficient. As a result, Riemannian geometry, a geometry of curved space that mathematicians had already developed independently, became necessary in its existing form. Physicists placed their ideas on top of the coordinates and tools that mathematicians had prepared in advance. The outcome of this union is Einstein's gravitational field equations expressed in a single line. In the world of quantum mechanics, the presence of mathematics becomes even more pronounced. Physicists such as Bohr, Schrödinger, Heisenberg, and Dirac actively drew on deep mathematical tools, linear algebra, group theory, and differential equations to explain a world in which entities are simultaneously particles and waves. Even when describing the state of a single electron, physicists do not rely on simple numbers. They use vectors and operators, and to explain symmetry, they must invoke abstract group theory. Modern devices such as semiconductors, lasers, MRI systems, and even the newly emerging quantum computers are all built upon this kind of mathematical language. In this way, mathematics is closer to a study that prepares in advance and in multiple layers the language and sentences that physics may later use.
Mathematicians broadly sketch possible structures and relations from the patterns found in nature, while physicists determine through experiments and observations which of those sentences are being used in this universe. The physicist Wigner described this kind of relationship by saying, "The usefulness of mathematics in the natural sciences is almost unbelievably remarkable." Put slightly differently, it can be said this way. Mathematics is the language that reads the secrets of nature, and physics is the work of using that language to construct a story about how the universe moves. Without mathematics as a language, physicists would have found it difficult to fully hold on to the images of the universe that arise in the mind, whether through words or through drawings. But if mathematics is at hand, the secrets of nature can be observed from a little farther away with a little more precision.